In this video, we'll be talking about the factor theorem, which will be our biggest help when it comes to polynomial division and polynomial factorization as well. So the factor theorem continues from what the remainder theorem told us. Namely, the remainder theorem told us that a polynomial that by plugging in k, our remainder is always what would happen if we divided x minus k into the polynomial. But if we got a remainder of 0, that would mean whatever the remainder was whatever the function value was. So a remainder of 0, meaning that this was a factor, would immediately mean that f of k must be a 0 for it. Okay? As the name implies, this actually improves upon the remainder theorem by helping us factor. So, for instance, let's go ahead and show that x minus 2 and x minus 3 are factors of this, and then we'll use that to find the remaining factors. Well, how can we see that it's a factor? Well, plug in 2, right? We can see here that by plugging in 2, you'll get 0. Namely, we see f of negative 2 equals 0. F of 2, sorry, is 0, and f of 3 are 0. You should check that. I'll just write check here. But what that means is we should be able to divide out evenly. If we plug in, if we do 2, doing 2 into there, and it's like synthetic division was pretty much designed for this. 2, 7, negative 4, negative 27, and negative 18. Doing the division out, we have the 2 comes down, 2 and 2 is 4, 4 and 7 is 11, 22, 18, 36, 9, 18, and look, a 0. But then that means that once we factor out x minus 2, we got this, right? So we can factor out x minus 2 out of here and get 2x cubed plus 11x squared plus 18x plus 9. But then we also know that this is we know that this whole polynomial had 3, x minus 3 as a factor. So we should be able to divide what remains by 3. So 2, 11, 18, and 9. Doing that, what do we have? Well, the 2 comes down, we get 6, 17. 3 and 17 is... something's wrong here. No, this is right. Why is it not working then? Oh, that's right. Okay. So 3, dividing 3 into here, we have 3 and 17 is 3 times 17, 51, 18 and 51, 918. Something is wrong here. Maybe it's positive 3? If we do positive 3, I think it might be positive 3. I think I put a mistake in here. So that would mean that was negative 3, which means f of negative 3. This is why you should really check this first. I'm being bad. The 2 comes down, we get negative 6 and 5. That would be negative 15. Yeah, that's what it is. It's x plus 3 is a factor. 2, 5, negative 15, 3, negative 9, 0. So now, in other words, we can factor out x plus 3 out of this. So x minus 2 times x plus 3. And what we have remaining is 2x squared plus 5x plus 3. Well, here it's not too hard to see that that's 2x plus 1 2x plus 1 plus x plus 3, I want to say. So I believe this factors as 2x plus 1 and x plus 3. Let's check that. No. Plus 3x. Well, no, there should be a 3 there. 2 and 3 is 6. Using that, 2x plus 3 and x. Let's try 2x plus 3 and x plus 1. I think that's right. We would get 2x squared first, outer, 2x, enter 3x, that gives the phi x. Yeah, that's right. Good. So x plus 3 and x minus 2. Good. There we go. So this is the full factorization. Okay? In other words, the big point of the factor theorem is that if you can figure out what our two factors are, if you already know some factors, you can divide those out to help you factor, okay? Bigger polynomials. Well, now let's have you try an example. So go ahead and show that x plus 3 is a factor of that and of this polynomial, and then find the remaining factors. On the count of 3, I'll reveal the solution. 1, 2, 3. So first, checking that it is a factor, we know by using the remainder theorem that means that plugging negative 3 into this should give us 0. Actually, that's a factor theorem, sorry. That's the whole point of this. The factor theorem tells us that we should get 0 out of here. If we plug negative 3 in, we do actually get 0. And then, of course, another way to see this is to just go ahead and divide and see if we get a remainder. So here we have plugging 0 in. We have what? If we plug 0, no, not plugging 0. Divide by negative 3, we end up with a 0 remainder, which means we can factor out x plus 3, and this is our quotient. And then we can further factor that to be x minus 5 and x plus 2. So we get this as our full factorization. This leads to an important closing note, which is, by guessing zeros, what we actually can do here, so by guessing zeros for this, we can actually divide out to get a smaller degree polynomial. Of course, as we saw with the last example, not this one, but the last one that I worked, you then get a smaller one, but then you kind of need to re-guess zeros. And basically the whole goal of this is you want to get down to a quadratic because we can always factor that. I mean, we might, of course, to be able to factor it, we might need to use the quadratic formula, but I mean, we have that. We don't have any other formulas for higher degree polynomials. For more practice in using the factor theorem, be sure to see pages 142 and 143 of the textbook and work problem 6 and 55 through 70. In our next video, we'll kind of talk about quadratics because we really need to consider complex numbers as well. Okay?